Section 4.7 is L'Hopital's rule, which is we're going to be revisiting limits. Now that we know derivatives, L'Hopital's rule is a way for us to kind of fix limits, certain types of limits that don't seem to work when we try direct substitution. It only works on some of them, though, and specifically limits that when we try direct substitution, we get an indeterminate form. So first, let's talk about what indeterminate form is. And I'm going to split this section into kind of two pieces. At first, we're going to look at some functions that are rational expressions. We're going to be finding the limit of some rational expressions. So our indeterminate form, or they're set up as fractions. So indeterminate form is when we get back 0 over 0, or positive and negative infinity over positive or negative infinity. Now, it really doesn't matter whether the infinity is positive or negative. Now, the 0 over 0 and the positive or negative infinities stacked like this in a fraction, they don't tell us what's going on with the limit. So typically, when we see 0 in the numerator, we think the answer is going to be 0. But when we see 0 in the denominator, we would say that the value of that fraction is undefined. When we see them together, it really means nothing. It doesn't mean 0 or undefined. It doesn't guarantee that there is a limit, and it doesn't tell us what the answer is either. We've got to do something different. Now, back in Chapter 2, when we got 0 over 0, that was an indicator that we had to do some sort of algebraic manipulation to fix our function and try again. And infinity over infinity was the same way. There was some sort of algebraic manipulation that we could do to fix that. And we would get infinity over infinity if we were doing a limit as x approaches positive or negative infinity. And both our numerator and denominator were a polynomial, obviously then they'd both go to infinity. So what matters really is which one is moving to infinity quicker. And when we use the word quicker, quickness is a rate of change. So the rate of change is really important to decide what the actual limit is. So how quickly our numerator and denominator are approaching these values is going to be really important to finding the actual limit. So just like in our first chapter, we're still going to try direct substitution for the limits. But if we see that we get one of our indeterminate forms, 0 over 0 or infinity over infinity, that is an indicator that we can use L'Hopital's rule, because if they're moving to these values at a different rate, the one that's moving there quicker is really going to determine our limit value. So how we decide how quickly they're moving is with the derivative. Derivative tells us rate of change. So L'Hopital's rule says that if the limit as x approaches a for f of x over g of x yields an indeterminate form, then the limit as x approaches a for f of x over g of x is going to be equal to the limit as x approaches a of f prime of x over g prime of x. We can take the derivative for each piece and try direct substitution again. If they're both approaching 0 or they're both approaching infinity, we need to see how quickly they're approaching. And the one that's approaching quicker is really going to dictate what the limit is going to be. So the quickness is going to be evaluated based on the derivatives. And if f prime and g prime are still going to 0 or they're still going to infinity, we could take the derivative again. We can do this as many times as we need to, as long as we're still getting an indeterminate form. So let's look at a couple of examples. The fraction form is actually really easy. There's another form that's a little bit more difficult, and that's when L'Hopital's, that's when our limit is in an exponential form. So again, back in our first chapter, we looked at this as a sign that we had to algebraically fix this. Now in this section, we don't need to algebraically fix this. We're going to use derivatives to fix this. So we're going to use L'Hopital's rule to evaluate each limit. And I want the limit as x approaches 2 for x squared minus 2x over 8 minus 6x plus x squared. So if you try to plug 2 in, we're going to get 4 minus 4 in the top, which is 0. And in the bottom, we're going to get 8 minus 12 plus 4, which is 0. So we get 0 over 0, which is indeterminate. So L'Hopital's rule says, fine, you can take the derivative and try again. So I'm going to do the limit as x approaches 2 for 2x minus 2. That's the derivative of x squared minus 2x. And in the bottom, the derivative is negative 6 plus 2x. And I'm going to plug 2 into that and see what I get. So if we plug 2 into the top, 2 times 2 is 4. 4 minus 2 is 2. If I plug 2 into the bottom, I get negative 6 plus 2 times 2. So negative 6 plus 4 is negative 2. 2 divided by negative 2 is negative 1. And it's that simple for the fractions. If you get an indeterminate form, we can take the derivative of each piece and try again. So let's try another one where we don't have two polynomials. The limit as x approaches 1 for the natural log of x over 4x minus x squared minus 3. If we try to plug 1 in, the natural log of 1 is 0, and then 4 times 1 minus 1 squared minus 3 is 0. That is indeterminate. So L'Hopital's rule says we can take the derivative of each piece and try again. So the limit as x approaches 1. Well, the derivative for the natural log of x is 1 over x. And the derivative for 4x minus x squared minus 3 is 4 minus 2x. Now if we plug 1 in, 1 over 1 is 1, and 4 minus 2 times 1 is 4 minus 2, which is 2. So we get a half. So we're really, since the original numerator and denominator are going to the same place, what we're really comparing is how quickly they're going, how quickly they're approaching 0, and that's going to dictate where the value is going to stop. And let's look at one with some trigonometry in it. The limit as x approaches 0 for 3 times the sine of 4x over 5x. If we plug 0 in, the sine, well, 4 times 0 is 0, so the sine of 0 is 0. 0 times 3 is 0. So we get 0 in the top, and in the bottom, 5 times 0 is 0, indeterminate. L'Hopital's rule says we can take the derivatives and try again. So the derivative for 3 times the sine of 4x, we're going to have to use the chain rule. So for any derivative, the coefficient just gets carried along. The derivative of sine is cosine with the exact same angle. And then the chain rule says we also have to multiply by the derivative of the angle. And then the derivative for 5x is 5. So technically, the 3 times the 4 can go together, and that's really just a coefficient of 12. So it's 12 times the cosine of 4x all over 5. Now if we try to plug in 0, cosine of 4 times 0, that's the cosine of 0, and cosine of 0 is equal to 1. So in the top, we have 12 times 1 is 12, and in the bottom, we have 5. So the limit is really 12/5. So anytime you get 0 over 0 or infinity over infinity, we'll do one more where we have infinity over infinity. You take the derivative and you try again. So let me see if I can find one where we get infinity. So this one might be a little tricky. The limit as x approaches infinity of x squared minus the natural log of 2 over x, all divided by 3x squared plus 2x. So if you think about what would happen if you plugged in infinity, now technically you can't plug in infinity. We just want to know where each of these pieces is headed towards at infinity. 2 over infinity is going to 0, and the natural log of infinity, or excuse me, natural log of 0 is going to negative infinity. Infinity squared is some giant number. So I've got infinity squared minus negative infinity. This is just some even bigger infinity. So we've got positive infinity here in the top. And the bottom, 3 times infinity squared plus 2 times infinity is infinity. So we've got infinity over infinity, which is indeterminate. So we are going to take the derivative and try again. So the derivative for x squared is 2x. To take the derivative of a log, you take whatever is inside of it and put it in a denominator, and then you take its derivative and put it in the numerator. So to take the derivative of that, you might want to think of it as 2x to the negative 1. That might be easier to deal with. This is 2x to the negative 1. And then its derivative, you're going to do the power rule on. So the negative comes out front, and the new power is one smaller. So it's negative 2x to the negative 2. And we're going to have to simplify that in just a second before we try anything else. The derivative for the bottom is 6x plus 2. Now, I'm not going to plug infinity yet. We need to work with that. Plugging infinity in now, I think is going to be useless because we really need to fix this complex fraction. So first of all, those 2's will cancel. The negative's not going to cancel, but the 2's will cancel. And if we simplify the x to the negative 2 over x to the negative 1, first of all, the negatives mean that they want to be moved. So this is going to flip-flop to x to the first over x squared. And we can get rid of the negatives if we flip them. And then we can simplify it and get rid of 1 in each spot. So that's really, and the minus minus can change to a plus. This is the same as the limit as x approaches infinity of 2x plus 1 over x. It's still a complex fraction. It looks a lot nicer now, but to fix the complex fraction now, I'm going to multiply through by the piece that's messing me up. Its denominator is an x, so I'm going to multiply everything by an x. So I've got 2x squared plus 1 over 6x squared plus 2x. Now if you plug in infinity, you're going to get infinity over infinity. Indeterminate. Take the derivatives and try again. Limit as x approaches infinity of 4x over 12x. Plug in infinity, you get infinity over infinity. Still indeterminate, which means you can take the derivative again. As long as it keeps being indeterminate, you can keep taking the derivative. Now we've got the limit as x approaches infinity of 4 over 12. There's no x's in there anymore, which means that limit is going to be 4 over 12, or 1/3. So that one was a little trickier because it involved some complex fractions, and it also shows you that we can use L'Hopital's multiple times on the same problem. You do have to make sure that every single time you try it, though, you keep getting it in indeterminate form. If it keeps coming out indeterminate, you just keep doing it over and over and over again until you get an answer. So, the fractional forms of L'Hopital's rule are a little bit easier. The exponential forms can be a little bit trickier. And pretty much any way that you could take zeros, ones, and infinities and write them in an exponential format is going to be an indeterminate form. So 0 to the infinity, 1 to the infinity, infinity to the 1, 1 to the 0. All of these, because they are limits, could potentially be indeterminate forms that we could use L'Hopital's rule on. Usually, and actually I'm going to take this last one off. Usually you would think 0 to any power should be 0, but then you would think if you raise anything to a really large power, it should get larger and larger and larger. So the idea here with the base and the exponent don't agree is the problem. 1 to the infinity, 1 to any power should be 1, but it depends on whether we're approaching 1 from above or from below. Since it's a limit, if we're approaching from below, that means we're approaching from values less than 1. We're approaching from decimals. And if you raise decimals to larger and larger power, they're going to go to 0. But if we're approaching 1 from above, if we're raising values bigger than 1 to larger and larger power, they're going to blow up and go to infinity. And then usually if you raise anything to the first power, you get back itself. But then if you have a very, very, very large number, it gets fuzzy. They're all limits. So the best thing to do is to follow this L'Hopital's rule, and whether you needed L'Hopital's or not will be evident within the first couple of steps. And what we're going to do right off the bat is we're going to get this out of exponential form. And there is a type of function that we learned back in algebra class that allows us to take this exponent and move it out of the exponent position. And that is a log. Logs allow us to move exponents to the coefficient position. So that's really going to be the trick here. And then once we do that, it's pretty much like what we did above. We're gonna have to just make sure it's a fraction, and then we can use the normal L'Hopital's rule. But then we're gonna have to undo that log at the end. So then you also need to remember that to undo the log, we need to know what the inverse operation of a log is, or the inverse function of a log is, which is an exponential function. We're gonna pretty much stick to just natural logs. So we're going to be doing ln. So we're going to undo the log at the end. And we're going to do that by applying an e, because natural logs and exponentials are opposite functions. So let me go through an example and show you exactly how we're going to do this. We're going to use L'Hopital's rule. To evaluate each limit. So let me get a few that have exponentials in them. The limit as x approaches 0 from the right, and you really don't need to worry about left and right when you do these problems. In order to make these problems mathematically accurate, we need to use right, but it's not going to change how you do the problem. So don't worry about the left and the right when you work the problem. Of x to the 2x power. The limit as x approaches 0 from the right of x to the 2x power. If you try to plug in 0, you're going to get 0 to the 0. Now, instinctively, just from arithmetic or from algebra, these two mean two different things. Usually, 0 to any power should equal 0, but anything to the 0 power should equal 1. So a base of 0 and a power of 0 mean two different things. So we need to see which one is approaching their value quicker. That's what L'Hopital's rule does. It says use derivatives. Whichever is approaching quicker is really going to dictate our answer. This is an indeterminate form, because the base and the exponent, their answers don't agree. A base of 0 means an answer of 0. A power of 0 means an answer of 1. So this is what we're going to do. I'm going to say y equals my limit. I like to set it equal to y to remind myself that I put a log in there. and then remind myself I need to take it back out at the end. So I just set my original limit equation or my limit expression equal to y. And then I'm going to come in and put a natural log in front of both sides. Now, there's some interesting stuff that can happen on this side. Technically, the log and the limit are interchangeable. Since this log is just an operation and it doesn't have an x in it, it can be inside or outside. And I would prefer for it to be inside. So I am going to switch them. And have my limit as the front of the right-hand side. And now I have a log with an exponent inside, and I can use properties of logs to move the exponent to the front. And these two are being multiplied. 2x times natural log of x. For L'Hopital's to work, I have to have a fraction. Back at the very beginning of this video, we said if we had a fraction of 0 over 0 or infinity over infinity, then we could use L'Hopital's and take the derivative of each piece and try again. Well, this is not a fraction. We need to create a fraction. I'm not going to mess with natural log of x and turn that into a fraction. That's just going to get ugly. But the 2x is going to be pretty easy to create a fraction out of. Instead of multiplying by 2x, we can always divide by the reciprocal. So multiplying and dividing by the reciprocal, or dividing and multiplying by the reciprocal are the same thing. We learn that in algebra, and we learn it when we first start learning about multiplying and dividing by fractions. So that's not only true with numbers, it's also true with variables. So instead of multiplying by 2x, I'm going to flip it and divide. So I'm going to leave my natural log of x on the top, and instead of multiplying by 2x, I am going to divide by 1 over 2x. That is the exact same expression. And I did that because if I plug 0 in now on the right-hand side, as x goes to 0 from the right-hand side in the natural log function, and you might need to look at the natural log function to see this, the y value is going to negative infinity. As x approaches 0 in the 1 over 2x function, and you might want to look at the graph of this to see it, it is approaching positive infinity. So it is indeterminate. Which means we can take the derivative and try again. So we have to have this fraction format in order for L'Hopital's to work. Now, sometimes when we pull that exponent out, like it's already naturally a fraction. So this is actually, I started off with one of the trickier ones where we had to create the fraction ourselves. But I'm going to think of this as 1/2 x to the negative 1 because I'm about to take the derivative. L'Hopital says take the derivative and try again. Well, the derivative for natural log of x is 1 over x. And the derivative for 1/2 x to the negative 1 is going to be negative 1/2 x to the negative 2. And I'm not going to plug 0 into these. I am going to algebraically fix this fraction first. This is x to the negative 1. So these guys both having negative exponents means they want to be moved. That one wants to go up, this one wants to come down. And dividing by a fraction is the same as flipping and multiplying. So this is going to be a lot of algebra really quickly. Dividing by a negative 1/2 is the same as multiplying by -2. My x to the -2 in the bottom is the same as a x squared in the top. X to -1 in the top is the same as a x to the 1 in the bottom. And we can do some simplifying here. There is an x in common in the top and the bottom. So that simplifies down to just -2x. Now when I plug 0 in, -2 times 0 is 0. That is not indeterminate because it's not 0 over 0 or infinity over infinity. That is not your answer. And that's why I write this. Y is the original problem. Y is the original limit. What I have found is natural log of y. Natural log of y is equal to 0. And I want to turn that back into what y is equal to. So to get rid of the natural log, we apply an e on both sides, because e is what will cancel off the natural log. And now we need to figure out what e to the 0 is. Well, e to the 0 is 1. So the limit is 1. So these exponential limits where we get an indeterminate form are quite a bit trickier. And I want to do one more. And this is actually B. And the next one I'm going to do is going to have some trig in it. So let's do the limit. As x approaches 0 on the right of tan x to the x. Tan x to the x. So the way that I do this, I like to set it equal to y. And that's because I'm about to throw a log in there. And I don't want to forget that at the end. Now I'm going to throw a log in there, and I'm just going to skip the step where my log and my limit change spots, and I'm going to go ahead and just do that from the get-go. Now, there's a property of logs that say the exponent can come out front as a coefficient. So the natural log of y is the limit as x approaches 0 from the right of x times the natural log of tan x. And if we have any hopes of L'Hopital's working on this, I would not mess with the log. I would mess with this guy and turn him into a fraction. So instead of multiplying, I would flip and divide. So the limit as x approaches 0 from the right of natural log of tan x over 1 over x. And let's see what happens to these guys at 0. Hopefully it's indeterminate form and we can use L'Hopital's. So the tan graph looks like this. So tan at 0 is 0. And then if you try to plug 0 into the log graph, we saw up here, the log graph at 0 is going to negative infinity. So if you're not sure about some of these really weird functions, just look at their graphs, because the answer to a limit is the y value. So this top piece is going to negative infinity. And then the 1 over x graph is very similar to the 1 over 2x graph. It's just doing things a little bit slower. So 1 over x, as we approach 0 from the right, is going to positive infinity. So it is an indeterminate form, negative infinity over and positive infinity. I told you at the beginning that the pluses and the minuses on those infinities did not matter. So now we can take the derivative and try again. So the natural log of y is equal to the limit as x approaches 0 from the right. In the top, the way that we take the derivative of a log is we create a fraction. And we put whatever's inside the log into the denominator, and we put its derivative in the numerator. So the derivative for the natural log of tan is secant squared over tan, and we're probably going to be able to simplify that sum in a minute, but don't worry about it yet. And then you're probably going to have to think of 1 over x as x to the negative 1 so we can take its derivative. The power rule is going to tell us that that derivative is negative x to the negative 2. And before you try to plug in again, let's try to fix this as much as we can. Secant squared over tan, and then the whole thing over negative x to the negative 2. I'm going to abandon my little equation here and just try to fix that secant squared over tan. Secant squared over tan. Well, secant squared is 1 over cosine squared. Tangent is sine over cosine. Instead of dividing by this fraction, I'm going to flip and multiply. And I can cancel 1 from each of those spots. Yep. So that turns into 1 over sine times cosine. So my numerator turns into 1 over sine times cosine. And negative x to the negative 2 is negative 1 over x squared. Instead of dividing by a fraction, I'll flip and multiply. And we've got negative x squared over sine x cosine x. So we took the derivative of the top and the bottom, and then we simplified it as much as we could. Now if we plug in 0, we get 0 over 0, because in the top, 0 squared is 0. In the bottom, sine of 0 is 0. So this guy is still indeterminate. And that's okay. We're just going to try it again. As long as it's still indeterminate, we can do it again. So the derivative for x squared is 2x. And then for the derivative of sine times cosine, we're going to have to do product rule. So I'm going to do the derivative of my first function times my original second function plus my first function times the derivative of my second function. So that's cosine squared minus sine squared. So I've got the limit as x approaches 0 from the right of negative 2x over cosine squared minus sine squared. And let's try again. Now if we plug in 0, I get negative 2 times 0 in the top, which is 0. In the bottom, cosine of 0 is 1. Sine of 0 is 0. So I've got 1 minus 0, which is 1. This is not indeterminate. 0 divided by 1 is 0. But don't forget, that is not our answer. That's what natural log of y is equal to. So I've almost finished the problem. Natural log of y is equal to 0. And now to fix that and get my final answer, I need to cancel off that natural log. And to cancel off the natural log, we throw an e in front of both sides. E to the 0 is equal to 1. So this limit is also 1, just like the last one.